All right, so this should be the last video from 12.3, double integrals in polar coordinates. So I want to solve this problem with you. Pause the video, take a moment, and try to wrap your head around it. Get your bearings. Okay, so I'm going to start with this equation, ironically enough. I want to be inside that. What is that? Well, somehow I think it would be beneficial for us to switch this thing to polar right away. X squared plus y squared is just r squared. X is r cosine theta, so I have r squared is 2r cosine theta. I'm going to cancel an r. You should ask yourself, why can I get away with canceling an r? I can, and I get r is 2 cosine theta. And now I can graph that in polar if I want to, or I can be a little bit sneaky and I can think about my equation back in Cartesian now, pull the 2x across, pull that over, and complete the square, and it's not hard to come up with x minus 1 squared plus y squared equals 1. So this equation is equivalent to this equation, and you know what this one is. This is just a circle centered at 1, 0. I'm going to put it there with radius 1. So that is, let's slide this up. All right, whatever. So that is actually what this polar equation gives you. It gives you circle centered at 1, 0 with radius 1. Okay, so now let's try and figure out what's happening in 3 space. I want to be under this guy, above the xy plane. That's fine, I've got that. This is just a paraboloid, and I want to be inside this. Notice this guy doesn't have any z's, so you're just viewing this stretched in the z direction. This is just a cylinder. So I want to be inside the cylinder, above the xy plane, and under this guy. Not too hard to picture this in your mind, perhaps a little harder to draw it. Let's do my best here. You're going to really see my lack of 3D drawing ability come out here, but we're going to make do as best we can. So there's that, and that's my paraboloid. And then I'm going to do the cylinder is sort of centered here, circle 1 is going to be there, and you can see what's happening. It's going to look like that. I want to be under the green and inside the red, so I'm going to be integrating up. I want to be inside the red circle, and I want to be underneath the green paraboloid. So here we go. To find the volume, what do? You integrate the roof. So here I'm integrating z equals x squared plus y squared, except that instead of writing x squared plus y squared, I'm going to go ahead and switch this to polar and just write r squared, and then I'm going to put my r dr d theta. Let's just jump and make that an r cubed. So it was r squared, r dr d theta. I'm writing that as r cubed. What's r doing? I'm going from 0, sitting here, and then as theta swings, r is equal to 2 cosine theta. What's theta doing? Let's look over here on my circle. This can be a little tricky for people. Theta is actually swinging from here around all the way up to here. So from negative pi halves to pi halves. So theta goes from negative pi halves around to pi halves. And at this point, you're set up. I'll point out to you that even though I just have an r cubed here, I cannot break this integral up into an integral in terms of theta times an integral in terms of r, because I've got a theta in the bounds. So what's this going to look like? You're going to end up with r to the 4th over 4, and you're going to plug in 2 cosine theta. It's going to give you cosine to the 4th theta. You're going to have to integrate cosine to the 4th with some constants thrown in. You're going to do that via angle reduction. I leave all that to you to avoid the length of this getting too long. And in the end, you're going to work this thing out and you're going to get 3 pi halves. So that is homework. I would like you guys to work that out. Pause the video if you want and make sure that you can do the mathematics and get 3 pi halves. But that is the volume that we're trying to find. So that's that example. I'm going to go ahead and take a chance on length and work out another example. This one shouldn't take too long. I want to find the area inside r equals 3 halves and outside r equals 1 minus cosine theta. R equals 3 halves is just a circle centered at the origin, radius 3 halves. You might have forgotten r equals 1 minus cosine theta. That's just a cardioid. I've drawn it in blue there. If you check out my polar review video, I'll have some examples that might help you be able to draw that yourself. You should have the ability to draw this graph in polar yourself and come up with the cardioid that I've drawn. So I want to find area. Interesting question. So I want to be inside the circle, and I want to be outside the cardioid. So just to be clear here, the area that I want is over here. I would take too long to draw it in nicely, so I'm just going to kind of scribble it on there. You get the idea. That's the area that I want. Good enough. How am I going to do that? How do we figure out area using double integrals? Double integrals give us volume. Well, if you remember in class, before we all parted ways, we said that if you want to find the area of the region R, it's the double integral over R of, you just integrate 1 dA. So I'm going to integrate 1 to get area, and I've just got to capture this region R in polar coordinates. Well, let's think about it. What on earth is happening here? So first off, I need to figure out what my radius R is doing. I'm going to try to draw it in blue right here. R is going from the cardioid to the circle. You can see that again and again. R is going from the cardioid to the circle. That's fine. What's theta doing? Theta is swinging from this intersection point, and it swings around to this intersection point. So what are those intersection points? Well, I'm just literally going to set this one as R and this one as R. I'm going to set them equal, and I get 1 minus cosine theta equals 3/2. So that tells me cosine theta is minus 1/2, and you can solve and come up with theta is plus or minus 2 pi thirds. So those are my angles, negative 2 pi thirds and pi thirds. And at this point, I'm ready to go. So let's write this thing down. The area A is double integral. R goes from the cardioid, 1 minus cosine theta, to the circle. That's what we said. Theta goes from negative 2 pi thirds to positive 2 pi thirds. I'm integrating 1. I switch to polar, and I get 1 R dr d theta. Again, I'm not going to work out the details for you. This is Calc 3 after all. You're going to integrate R, you get R squared, plug in your bounds, you'll have a cosine squared, you'll have to do the angle reduction formula. I'd like you guys to work this out. Pause the video if you want, work it out, and you should come up with 9√3 over 8 plus pi halves. And so that wraps up my videos for section 12.3. I've posted an updated version of the homework problems on Campus Web and also Microsoft Teams. I would just mention to you that I've cut a few problems out of the homework. So you'll always want to check the updated version every time, essentially, because I'm going to be changing it as we go along.